Okay, it's been a while since I made a video. I'm going to now make a video about how to use the practical summaries and do the first practical summary. So if you go to the web page at the address here in the address bar, you'll see that there's a folder with practical summaries, and going in there you have practical summaries available for several of the chapters in the notes. Today I'm going to start off with the practical summary for chapter 12 on numerical optimization. Okay, so if you've downloaded the code and all as explained in the previous videos, I showed how you could use the VS Code editor to work with the code. As a reminder, if you don't have the econometrics project open in a folder, you can open a folder. You need to go to wherever you have the code and highlight the econometrics project. I have it right here, highlighted in blue. I add that. Okay, and at that point here in the Explorer, right here, these double folders here, that is the Explorer pane. You can see we've got the econometrics project opened up. And there are a number of subdirectories here, one of which is practical summaries. If we open that up, we've got the optimization summary for chapter 12 right here. Okay. So I open that up. One thing you want to check to make sure before you run this is that you have the econometrics environment activated here. Okay, down here where I'm messing around with the mouse. You can see the environment, and if you don't have the econometrics environment activated, then you can select it here, or if you need to find it, you can go off and pick and choose it using the folder selector. Okay, but I've already got it going, so I'm going to just leave that be for now. Okay, remember in VS Code, blocks which are delimited by double hash marks can be run using Alt-Enter will run the entire block, and Control-Enter will run a single line. Okay, so in the first block I've got here, this is defining some data. It's creating X and Y data for linear regression, and it's computing the OLS estimator. Now remember that the OLS estimator minimizes the sum of the squared residuals, so that's an optimization problem, a minimization problem, and we have the analytic solution for OLS. So this is going to give us a baseline problem to compare to, which will allow us to check that numeric optimization methods can obtain the actual solution. Okay, so if I press Alt-Enter to run that, it's going to appear here in a little bit. The first time we run code in VS Code, it has to get the language server pre-compiled, so it's taking a little while for the first bit, and that won't be a problem as we work through though. Okay, so here we have the results for the two parameters in this model. The parameter estimates are 9.16 and minus 0.82 are the OLS intercept and slope parameter estimates. Okay, so that's the analytic solution to the minimization problem. So now chapter 12 is about numeric minimization, which we need to use when we don't have the analytic solution available. Here we're going to use the fmin-unc function, which is part of the econometrics code, to do a numeric minimization. Now that function requires that we define the objective function. One of its arguments is the objective here, and the previous two lines are defining the objective function. So line 21 here is computing the squared residual for the ith observation. Okay, well, that's a vector of the squared residuals for all of the observations, sorry. And then line 23 is computing the mean of those. Okay, so that means that our overall objective function is the average of the squared residuals. Okay, and line 23 here is doing the minimization. Okay, pressing Alt-Enter will get the solution. And right here you have the solution we obtained with a convergence message of true. Okay, so the the values that we obtained as the solution are the same as what was obtained by OLS. Okay, so that means that this numeric minimization actually worked. Now, fmin_unc is just a convenience function that's in the econometrics code designed to emulate the input format of minimization functions in MATLAB, and that's because I teach students who are some of them are more interested in using MATLAB, but I want to have my Julia code accessible to those students as well. Of course, we can just directly go and use the Optim package for Julia and the limited memory BFGS algorithm. That's what fmin_unc is wrapping up for us. So using it directly, which gives you a little bit more knowledge of the controls that you have available, can be done in the way we're seeing here in this block here. So pressing Alt-Enter, we get the solution. Actually, the output of Optim doesn't actually show you the solution. It tells you some information about the iterations and so forth. To actually see the solution, we need to use what we see in this line here. I'll press Alt-Enter again, and there's the solution. Okay, and you can verify that that's the same solution that we have up above here. Okay. So that just shows you how to directly use Optim rather than the fmin_unc wrapper. One thing we want to check when we're trying to do a minimization is that the solution is actually a minimizer. So we want to check the definiteness of the Hessian matrix at the solution we found. That's what we're doing here. We're using the forward diff automatic differentiation package to compute the Hessian in line 44. Okay, I'll press Alt-Enter to do that. That Hessian is being computed at the point beta hat, which was the solution that we obtained up above here. So we're computing the Hessian at the minimizer that we found, or at the point that we found as the potential solution. Here's the Hessian right down here. That's something that you can actually compute analytically if you want. So you see that we did get the correct Hessian. And what we want to do is verify that the Hessian is positive definite. So in line 47, we're computing the eigenvalues. So I press Alt-Enter to execute that block. And here you see the two eigenvalues of the Hessian. They're both positive, and that means that Hessian matrix is positive definite. And that means that the solution that we computed is a local minimizer. Now, of course, the objective function is the sum of the squared residuals, and we can analytically prove that that is a globally convex function, which means there's only one minimizer, and therefore the minimizer that we found is the global minimizer. Now, unfortunately, though, in many cases we're dealing with objective functions which may have multiple local minima, and the next block defines such an objective function which has several minima. Okay, I'll press Alt-Enter to define that. Okay, let's see what this function looks like. That's what we're doing in the next block here. Okay, press Alt-Enter to run that block to see a surface plot. There's a warning here, which I'm not quite sure what's going on there, but we don't need to worry because we do get the output we're after. Here you can see, if you spin that around, you can see that there are 3 local minima. Okay. And down here in the next block, we're looking at a contour plot of the same function. And you can see a little bit more clearly that there are 3 local minima. One's right here, around the, you can see that x value is about 0.01, y value is 1.5 more or less, and the objective function value is minus 4.7 there. And there are 2 other local minima, and if you look at those, you see that the z value is not as low. So those are local minima, and this one here is the global minimum. There are 2 local maxima as well here. Okay, so that's the type of function we're looking at. Now notice that the way we define the objective function up above is in terms of the x and y coordinates. Okay, but when we're trying to do a optimization using optim or fminunc, we want the arguments to be in a vector rather than as in a list of arguments. Okay, so Julia's multiple dispatch allows us to define a method where the argument coming in is a vector, the vector theta, and then we decompose theta into its two elements here in line 87, and then we can just call the previously defined function to evaluate the function at those coordinates. Okay, so that's an example of multiple dispatch, which is quite a convenient feature of the Julia language. Also, remember that when doing numeric minimization or optimization in general, having the elements of the gradient being on more or less the same order of magnitude is very helpful. So what we're doing in this next block is checking the gradient vector computed using automatic differentiation here in line 103 at some the point at the vector theta start, where theta start here is just a randomly generated point. So if we run that a few times, Alt Enter here, we'll see the gradient at several random points in the parameter space. Now, the important thing to notice here is that the elements of the gradient are roughly of the same order of magnitude. They're off by approximately a factor of 10 here. Okay, so it's pretty close. I'll run it again. Here they're on the same order. And if we run it a few times, you see that basically for points throughout the parameter space, the gradient vector is always more or less on the same order of magnitude the elements are, which means that we don't have this scaling problem that you sometimes have. It's good to check this sort of thing because that is a very common source of difficulties when you're trying to do numeric minimization or optimization. And remember, the solution, if you find that you have a problem, is simply to rescale your data. Okay, so the next block is doing the optimization. It's going to plot the contours, and then it's going to compute the optimizer using a random start value, and it's going to plot the optimizing point on top of the contours. So I'll run that one time. Okay, remember that this point up here is the global minimizer, and in this case, with that first try, we found the global minimizer. Okay, I'm going to run this block a few times to show you that we don't always find the global minimizer. In the second run, we're down at a different point, so that's a local minimum, but not a global minimum. We found the third one on the third try. That's just a coincidence again. Okay, now I'm pressing Alt-Enter, and the thing jumps around every time I do it. Now, one thing that I want to show you, if I do this often enough, is that occasionally you zoom off into some place very far away. What's happening there is that the objective function is approximately flat out there, so the gradient vector is roughly 0, and we don't have any way of getting back to where we want to, where the actual, we're far away, and the local properties of gradient-based minimization, we can't work our way back. So that's something that you have to be aware of, that occasionally slight numeric difficulties can make you take a large step, which can take you far away from the actual region where the minimizer is actually found. The next block down here is to use an alternative algorithm which uses box constraints. If I know that the reasonable parameter values are contained within some box, I can impose that constraint, which can keep me from seeing this type of problem which we just encountered of ending up zooming way outside of the box and being unable to get back. So if I have some sort of knowledge of the possible range of the parameter values, that's what I'm using right here in these two lines. This is just invented information, but sometimes an economic model can give you plausible values for parameters. So if you can reasonably impose box constraints, this method shows you how you can do that. So we define the constraints there, and then I'm going to pass in those constraints, and I'm going to use the fmin box algorithm of Optim, which will keep me inside of that defined box. And when I run that, using Alt-Enter, I'm always going to stay within the box. Now that doesn't mean I'll find the global minimum every time. I still have the problem of the multiple local minima, but at least you'll find that if you run this repeatedly, you never zoom way outside of the relevant region. Okay. Another possibility when we have multiple local minima. Okay, so we've seen that in this problem we have 3 multiple local minima, and if I run the gradient-based method often enough, I do find the global minimum. Okay, so when the objective function is reasonably regular with a limited number of local minima, then by using enough start values and running the algorithm enough times, you will find the global optimizer. Now, unfortunately, we sometimes have very complex objective functions which have many local minima, and that strategy may not be successful. That's when you might consider using a global minimizer, such as the simulated annealing method, which I discussed in class. And this block here shows you how you can use simulated annealing. Okay, you need to define a box constraint, as in the previous example, which as is done here in lines 163 and 164. And you also need to define the temperature reduction parameter of the simulated annealing algorithm, which is what we're seeing in 162. Then this line here, 166, is actually calling the algorithm. Okay, there are additional arguments to this algorithm for fine-tuning, but these are the temperature reduction is the most important parameter of that method. Okay, Alt-Enter to run it. The parameter values here, you can see, are close to 0, 1.6, so we did find the global minimizer. Okay, run it again. Alt-Enter. Okay, I'm running it a few times. You can see that this global minimization method is always going to the same point, which is the global minimizer. Okay. That doesn't necessarily happen if you make the temperature reduction too quick. If I put that at 0.05 rather than at 0.75, if I run it again, well, it's still working pretty well. There we go. It converged to one of the other minima in that run there. Okay, so the temperature reduction is the most important parameter in simulated annealing. As long as it is slow enough reduction, which means if RT is close enough to 1, you've got pretty good guarantees of finding the global minimum. Okay, that's all for this video.